All right, thank you, Sasha. So we got quite acquainted with the northern part of the East African Rift from the past two talks. And so let me take you a little bit south and a little back to back down to an early stage part of the rift. So the motivation for this talk is the general overarching question that we always have about rifts, which is what is the role of magma in strain accommodation? Specifically, do magma and magmatic fluids contribute to dilatation in earthquake sources? So I look at earthquake sources using seismology, and how does the magmatic system contribute to the crustal state of stress? So I do a little bit of modeling afterwards. So this is the East African Rift. We were here earlier around in Afar in the main Ethiopian Rift. It goes down to here, the Western Rift and the Eastern Rift, and actually continues down to a Southwestern Rift down to Botswana, and probably a Southeastern Rift here going down to Madagascar. And my study area is here, the North Tanzania Divergence Zone, composed of the Magadi, Natron, and Manyara Basin. There's also the Eyasi Basin and the Pangani Basin off, but I focus on these three basins here in the middle. And this is located just by the Kenya. So north of this line is Kenya and south is Tanzania, just by the border. This is the most seismically active sector of the Eastern Rift. As you can see here is double difference earthquake locations from a local seismic array deployed there in 2013 to 2014. And this temporary local array enabled us to study the area in detail. The Natron Magadi basins also represent the region of highest estimated tectonic degassing of mantle carbon dioxide in the East African Rift, from about 2 to 6, almost 6 megatons per year. And it has been a region of persistent carbon-rich magmatism for approximately the past 4 million years. Oldonyo Lingai, right here, and right here in this cross-section, is the only active natural carbonatitic volcano is found in this area. This carbon from the tectonic degassing and from the carbonatite volcanism in the area must be sourced from laterally advected cratonic lithosphere, and then finds fluid pathways to the surface that then result in the elevated levels of diffuse soil degassing. The same area was host to a dike intrusion in 2007. So there's the Oldonyo Lingai, and that's Galai right next to it. The dike intrusion in 2007 was accompanied by an earthquake swarm and effusion at Lingai, which then transitioned to ash eruptions. This 2007 diking here was probably sourced from a silt complex above a magma chamber, as imaged and interpreted from gravity and seismic joint tomography by Raker et al. And seismicity patterns from Weinstein et al. This area also shows a very interesting local stress rotation. So here we have summed moment tensors, some focal mechanisms from these different regions in the area. Black beach balls represent summed teleseismic earthquakes dating back to 1964, while the blue beach balls are from local earthquakes from the 2013-2014 local array. And we see that earthquakes from this middle bit, the box that contains Oldonyo Lingai right there, and the southern part of Galai, where the dike also occurred, this area shows a north-northwest extension, while the general area, regional extension in the area from GPS relative plate motions is roughly east-west. So we observe almost 60-degree local stress rotation in this small area here relative to the region. And so I performed waveform modeling on the biggest earthquake, so greater than magnitude 3.5, as recorded by the local array to study the source mechanism represented here by the beach balls. These moment tensors have different components, so they're full moment tensors. So not just double couple, which is pure shear sliding on a planar fault, which would plot here on a source type plot right here in the middle. It also includes an isotropic component, compensated linear vector dipole, and C here means crack. So these earthquakes, the largest earthquakes from 2013 to 2014, show strongly non-double couple sources. And this is also confirmed by bootstrapping. So this is a bootstrapped set of solutions for event A here, which was a magnitude 4.7 earthquake. And event B was also 4.7, so we're mostly interested in these two larger earthquakes, and they're very similar, and they both have significant non-double couple components. And so we interpret those non-double couple earthquakes to be fluid-involved faulting above a sill complex, the sill complex that I showed earlier. But there are only a few earthquakes, as you can see here, that were of large enough magnitude for detailed waveform modeling study that was recorded during that time period, 2013 to 2014. And my question was, are these related then to the 2007 earthquakes and the 2007 diking? And to answer this, we look at data from a nearby permanent station, and we use template matching. So the nearest permanent seismic station is about 200 kilometers off to the north, Cambio. And I perform waveform cross correlation with that station, with the waveforms of that station, comparing earthquakes from the 2013-2014 time period to all other earthquakes recorded in the area, in the earthquake catalog. And we find that yes, the 2013 earthquakes match some of the 2007 earthquakes, and discovered two other earthquakes that also matched. So here we have the three components of the earthquakes, bandpass filtered to the frequencies we use for waveform modeling. The regional locations of the earthquakes here are about 20 kilometers off because of the sparse permanent array in Africa. And we propose that these earthquakes all occurred above the sill complex. They are similar but not identical, which can be expected in magmatic regions where strain is distributed over fractures above the intrusion, as opposed to slipping on the same fault. We then conclude that magma-involved faulting persistently accommodates strain over intereruptive cycles. So we know there must be a transcrustal magmatic system with a lower crustal magma chamber and shallower sills underlying this magmatic system, with fluids such as CO2 probably using faults as conduits to the surface. So how does this magmatic system contribute to the crustal state of stress? And can it explain the local stress rotation that we observe? So I compiled data from tomography, refraction studies, gravity, and to build and constrain the geometry of 2D and 3D finite element models to determine the relative contributions of different rift components with a stress or a strain field. So here are 2D models, considering here the effect of, separately, the effect of, for example, here surface topography, the effect of an intruded seal, an inflated magma chamber. This is a thin crust, so the moho would be somewhere around here, thinnest point around here. And this is all the four components added together and all the components with extension. And we note how the moho effect here is very large at depth. but there is still a significant effect here and the shallow bits from the surface topography and the shallower magmatic stresses. And so here's 1D profiles through the middle of those 2D plots for vertical stresses and horizontal stresses. And we find that surface topography influences shallow stresses, shallow stress location. But subsurface density contrasts here, so the effect of the inflated magma chamber and the moho, the thin crust, play a larger role at strain localization at depth. And the 3D models of this also produce the local stress rotation that we observe.
Can you hear?
Yes?
Can you hear me now?
Yes. Hello? And so we conclude that also that large subsurface stresses are important for the 3D understanding of rifts. And so just to sum that all up, we conclude that earthquakes occur across a swath of faults and tensile cracks above the sills and respond to regional extension, as well as inflation and deflation from the underlying magma chamber. And the local stress field is due to an interplay between topography, subsurface, magmatic stresses, and regional extension in this early stage rift. Thank you.
Thanks a lot. It was a great talk, despite the small interruption. Do we have some questions? Chat. You mentioned some 3D models. I'll just start with one question. You mentioned some 3D models to explain the map view stress rotation. Was that right? Could you say a bit more on this?
Yeah, so it's a figure with a lot of things going on. That's why I didn't put it, and I wanted to just summarize all the results. But what it shows is that there's, by putting together the different components that I mentioned, you can actually not just topography, not just each component separately, but the interaction of all of them creates this rotation, a local stress rotation that matches the focal mechanisms in the area of study, of interest.
But you have an image of it? You have a model that shows this, or is it just speculation for now?
I do have a model that shows this, so I'm just going to quickly. Did I share that? Am I sharing?
It looks good.
Yeah, so this is the map view, but it's usually a lot to take in without a lot of time to look at it. But here you can see that in this area, there's this rotation. So this, ignore the right part, this second column is the lower crust, but this is the upper crust. And you'll see that if I'm only modeling topography here, the extension is still kind of maybe east-west, a little going this way, about northeast, southwest. But once I put in all, including the moho and the inflated magma chamber, all the components in, that rotates to about north-northwest, which matches the seismicity in this areas, in the southern part of Pagalay area.
Okay, thank you. We have another question. Just dig that out. Gianrito.
Yeah, how much extrusive relative to intrusives do you have, and where is the magma localized, or and what is controlling the extraction of the magma?
Okay. So how much extrusives? The diking did not reach the surface. So this diking was confirmed through INSAR and seismicity. So most of the magmatism in this area is intrusive, except for eruptions at Oldunyolingai volcano currently. So most of the magma we think is emplaced at about below 8 kilometers depth. I think that's around 6 kilometers depth, where there's a lot of seismicity occurring. I just want to share that real quick. So right around here, where the seismicity is all occurring. So that's the depth that we constrain the sill complex to be. So that's where we think a lot of the magma emplaced, the shallower bits are. And your last question was about something about magma extraction. How often was that your question? Could you?
No, the question is what is actually controlling this extraction? Is it tectonic, or is it the rheology of the crust, or are there some layers that are controlling it, or the density of the crust, or?
So what's controlling the magma extraction? I would say it's the interplay of a lot of things. There must be magma pressure from below that pushes magma up to the surface, but it's also facilitated by extension in the area and tensile cracks in the area that helps magma find pathways to the surface. With that said, I can't really say anymore with like how much exactly for each component, how much each component helps in magma extraction.
Okay, thank you. One more question from Giacomo, and then we move on to the kind of summarizing discussion.
Yeah, just a quick question about the role of pre-existing structures in this area. Do you see any control by these inherited structures on the, for instance, the reorientation of the local extension? Or?
So we're under the impression that pre-existing lithospheric weaknesses structure is not a major component, because the fault, the strain fabric from previous tectonics in the past in the area might look reasonably oriented from map view, but they are dipping too shallowly. So it's not really, in a 3D sense, it's not the current state of tectonics in the area is not really just taking the old pathways, taking the old fabric, because the dip in the third dimension sense is not right.